Hi class. We already looked at using pKa to predict acid strength, and that was pretty straightforward if we have the numbers at hand. But let's say we don't have the numbers in front of us. How are we going to make a decision between two or more acids, which is the strongest? And that's where we're going to need some structural things to look for. So we're going to go through a series of rules. I call them the ARIO rules. Okay? And A stands for atom. The atom bearing the hydrogen, right? And then resonance for resonance, or R for resonance. You're familiar with resonance, so is the conjugate base stabilized? Okay. Then we have I for induction. Are there any nearby electronegative atoms? That will be stabilizing as well. And then O is for orbital, right? And this has to do with hybridization of the atom with the acidic H. Okay, so ARIO rules are going to really help us in predicting the strength of an acid. So let's start with the first rule, atom. Okay, atom is talking about the atom bearing that acidic proton. So I've highlighted the acidic proton in pink here, and these atoms, carbon, nitrogen, oxygen, and fluorine, are all from the second row of the periodic table. And I have the pKa's listed below here. So we have a very weak acid with a large pK and a stronger acid, although by our classification it's between 0 and 11, so this is still a weak acid. All right, so what can we use to explain this difference in acidity? Well, if we think about general chemistry and our periodic trends, there should be a few that might stick out. So you might be thinking about electronegativity, or you might be thinking about atom size. And both of those are going to be helpful when we're looking at this atom rule. So when elements are in the same row of the periodic table, electronegativity rules. Okay? Carbon is the least electronegative of this grouping, and fluorine is the most electronegative. So what does that tell me about the conjugate base? So I would end up with CH3 minus, NH2 minus, OH minus, and F minus, right? So if F is the most electronegative, that means, well, electronegativity, first of all, is the affinity of an atom for electrons. So if it has a high electronegativity, it wants those electrons more. So fluorine, being the most electronegative, is going to be happiest, quote unquote, with these excess electrons because it has a high affinity for electrons. Followed by hydroxide. Oxygen is the next electronegative, so it's going to be the next most stable, followed by nitrogen. And carbon, being the least electronegative of this grouping, is going to be the least stable of these bases. Okay, and so if we have a less stable base, we end up with a weaker acid. Okay, so there is a connection between stability and basicity and acidity, right? So if this is unstable, high energy, it's going to be pretty reactive. It's going to want to get that proton back. And if it has that proton, it's not going to want to give it up because this is not very stable. Okay? The more electronegative, the more stable the conjugate base. The more stable the conjugate base, the stronger the acid. So there's a couple different ways you can frame it. You can frame it going forwards or backwards, okay? So make sure you wrap your heads around those. Strong bases, weak acids, least stable, most stable, stronger, weaker, okay? Because of electronegativity when the atoms are in the same row of the periodic table. Next, let's look at atoms in the same column of the periodic table. For this series of compounds in the same column of the periodic table, we have a different trend here. So F to I, we're getting less electronegative, and here we're getting to be stronger acids. So that's converse to what we just said previously for atoms in the same row. So there must be something different that we need to use to explain the difference in acidity for atoms in the same column or same group. Okay, so we're looking at their conjugate bases, F minus, Cl minus, Br minus, I minus. The more stable the conjugate base, the stronger the acid. So if this is the weakest acid and this is the strongest acid, that must mean that I minus is more stable than F minus. So what could we attribute this stability to? Okay, can't be electronegativity because fluorine is the most electronegative. Well, what about atom size? Okay, the trend moving down the group is increasing atom size. So would a larger atom be more stable with a negative charge? Think about that. If we have a larger atom, we have a larger electron cloud and a larger region of space for that extra electron to occupy. So that charge is spread out over a larger surface area, over a larger volume of that atom. And so yes, size does contribute to the stability of ions in the same group. Okay, so HI is the strongest acid because I minus is the most stable because it's the largest atom. Okay, so strongest acid, largest atom, weakest acid, smallest atom. All right, so when we have atoms that are attached to acidic hydrogens that are not in the same group or the same column, size is going to be the determining factor. So if we're comparing, say, NH3 to HCl, we see that chlorine is lower on the periodic table than nitrogen, so the atom size is going to be the determining factor here. Cl minus, being a larger ion, is therefore more stable than NH2 minus. Okay, so you have to consider the atom that bears that acidic proton. Is it in the same row or the same group? Do they have anything in common, right? So electronegativity in the same row, size in the same group, and if there's nothing in common, then it's atom size. Okay.